All right. Good evening. Black Forest Cross Country Soaring Series. Um, this evening, we're talking about collision avoidance technologies. So we're on our way. So our seminars so far, we're March 26th for collision avoidance. We got three more after tonight. So, and for everybody, since we may have some new folks here, presentation download is available on the members SSA website. Under You can see it there under my homepage, news, resources, and then webinars. Generally, the webinars, both the recording and the slides will be available sometime later, uh, you know, either later this week or very early next week. That's our usual goal. Again, we need to thank the SSA for making the webinar software available for us to do this. And the other one is we need to thank Frank Whiteley because he's our little gnome running around in the background to keep things working. The live slides are our live presentation is eligible for Wings credit. We have three members of our club that are part of the FAA safety team. And these folks work in the background to make sure that you get Wings credit. When you signed up for this seminar, you should have used the email you use for signing into your Wings account. If you did, it will automatically be added. If you used a different email account, email me and I'll forward, with both emails and I'll forward it on so we can get that accounted for. I did have someone last week said that they didn't get their credit. And if you're on tonight, send me your email again. Somehow it disappeared from my system. You know, fun little gremlins. And we have
Hey,
instructors.
sorry, excuse me for jumping in, but people need to stay for at least an hour to get credit. So that could be a reason why they didn't get credit.
Ah, okay. Um, so now we have some of our Black Forest instructors are hiding in the background. Our pool are these four people. We have generally one, two, or three of them available in the evening. They'll answer questions that you ask using the Q&A function. And we will have a Q&A session at the end of the presentation. And if the question looks like it might have a uh, need broad attention in the middle of the presentation, one of them will uh, jump in and we'll address, if it's that important, we'll address it at that moment. So, collision avoidance technologies. We should be right around 2 hours this evening. Uh, this one, in addition to uh, how it works, this one is, heavily safety oriented. Um, this is, we're working to describe the collision avoidance technologies. We'll describe some of the system examples, but the biggest thing about all of this is, you know, we don't want things to go bump in the night. It was interesting. I've often, back even close to 50 years ago when I was getting my private license in power, it was said that FAA regulations are often written in blood. Air traffic control is definitely one of those situations. Starting in 1952 was the first time that radar was used in terminal areas. Of course, this was generally military surplus equipment and it wasn't optimized for air traffic control. It was what is called a primary surveillance radar. It did not require any installed equipment on board the aircraft. It was, just like the stuff they used during the Second World War. In 1956, there was a Grand Canyon, Arizona midair. It was a United DC-7 and a TWA Super Constellation. June 30th, 1956, the two aircraft collided over Grand Canyon National Park. 128 people on board both flights. It was the first commercial airline crash that resulted in more than 100 deaths. The collision took place in uncontrolled airspace. Back at that time, if you were out of the terminal area and you were above a certain altitude, it was the pilot's responsibility to maintain separation, what we call see and avoid. In 1958, near Las Vegas, a DC-7 and a U.S. Air Force F-100F, early in the morning, 8:30, clear skies, excellent visibility, you know, something like 35 miles. The flight paths of the two aircraft intersected about 9 miles southwest of Las Vegas. They collided at near head-on and estimated closure speed of like 665 knots. The problem here is there were two agencies controlling the aircraft, Air Force and the FAA, or whoever was air traffic control at the time. They were not communicating directly with each other. It's also believed because remember back in that time period, those aircraft had a lot of window frames and stuff like that, that structures in the windscreen of both aircraft may have blocked the view of the other aircraft. And so as we look across, the result of that one was in 1958 is the transfer of all national airspace systems, that's what NAS is, air traffic control went to the FAA, and then they upgraded the ATC systems and the software. So there's the first change as a result of one of these accidents. In 1960, the concept of transponders were introduced with something called secondary surveillance radar. And don't worry about those. We'll cover that stuff here in a couple of minutes about what all that means. We come into 1967 in Dayton, Ohio. We had a DC-9 uh, and a VFR Beech Baron. And since 1961, the FARs had mandated speed restrictions below 10,000 feet within 30 miles of a destination airport. Okay, that was a result of another midair collision. By 1970, after the Dayton accident, all aircraft in all areas below 10,000 feet were prohibited from exceeding 250 knots, indicated airspeed. The Dayton accident also contributed to the FAA's decision to create terminal control areas, or TCAs. Basically, the B airspace, what we call B airspace these days, around the busiest airports. Now, interestingly, the accident at Dayton pushed them down this path. Dayton didn't upgrade to anything until it got Class C airspace in the late 1980s. It's just little interesting side bits that hang out there. In 86, I think probably a lot of us remember this when it was Aeromexico DC-9 over Cerritos, California, and a Piper Cherokee went bump. The results of this accident and some other near midair collisions, I always love that term. In terminal control areas, the FAA required all jets in U.S. airspace be equipped with a traffic collision avoidance system. You've probably heard the term TCAS. And it required all light aircraft operating in dense airspaces to be equipped with Mode C transponders. And the Mode C transponder was the one that reports altitude. So so carrying that into 87, so the TCAS and Mode C. You have to understand that ATC's current collision avoidance system or approach is about avoiding collisions involving large passenger aircraft. Further, the focus is on aircraft operating under instrument flight rules, regardless of the weather conditions. Now, what we have today in 2020, the ADS-B system is now required in the airspaces that previously required transponders. So we have the more advanced, and that was the 2020 mandate. So when we're looking at collision avoidance, we're trying to prevent things from going bump. It's a recognition that the big sky model is inadequate for aircraft separation. Remember, our interest is airplane to glider and glider to glider. there's this recognition that see and avoid is no longer a sufficient methodology, that if we can get some assistance from automated systems, if we can get some assistance from other folks. One of the things that we run into is we have large number of gliders concentrated in a small area. So we've got thermaling, we've got blind spots in our gliders. And the other one, especially for ridge soaring, we have this high-speed head-on closing flight. And so the recognition that we need some assistance for our pilots. Now, air traffic control-based collision avoidance. Again, we're based, ATC implementation is based on potential collision conditions being detected on the ground-based systems with warnings issued to the involved aircraft by ground-based air traffic controllers. All right. If the ATC controller cannot see a problem, there's no warning. If you aren't talking to ACT or to ATC, there is no warning directly to you from them. So our transponder requirements are primarily for high density traffic areas and IFR separation. Gliders are still currently exempt from transponder requirements and ADS-B out requirements. What we've done as a community is voluntarily installed transponders to improve our visibility to other National Airspace System users. Air traffic control does see glider activities, and aircraft with TCAS or the other system called ACAS for Airborne Collision Avoidance System can get warnings, can get warning indications directly. One of the things that happened relatively recently is we now have a nationwide transponder code. It's 1202. This is a VFR code only for gliders, and using this code, you are not required to maintain radio contact with ATC. Now, come back around to non-ATC based collision avoidance. The on the box on the left, we're talking about why ATC-based collision avoidance really isn't adequate for glider operations. We do not fit the ATC models for aircraft operations. We're not a point A to point B transportation mechanism. Okay. The equipment limitations, for instance, the transponder resolution is insufficient to provide aircraft separation. For instance, formation flights, in our case, a glider on tow. ATC will tell a formation flight, like you've got three of you going close formation and flying up to Oshkosh. They'll generally tell the flight to only have a single transponder responding for the entire formation. Or in our case, they want that, if we've got it in tow plane and the glider, like at our club, we use the transponder in the glider for the formation flight, and then bring on the glider's transponder once we've gotten off tow. And the reason for that is when two aircraft get close enough together and they've got transponders, the signal gets muddied back to the ATC system. They can't tell the difference between the two. This is one of the reasons that it comes up, and I'll have something specific later, but this is why, for instance, ADS-B is considered situational awareness, not collision avoidance in the cockpit. And then obviously the majority of ATC personnel are not trained in glider operations. And if we were trying to get assistance from them, that would increase the workload on the ground-based assets. So what's been developed for non-ATC collision avoidance is a peer-to-peer system where the gliders are interacting directly with each other without pilot intervention. We don't have to make a radio call. The system was designed with a resolution that's adequate for close quarter operations. It is working with predictions of aircraft movement behaviors. Am I thermaling? Am I flying in a straight line? Have I pulled up? Those kind of things. And the alerts are presented directly to the pilot in real time. So this is the FLARM system there that is installed in an awful lot of our aircraft, and we'll be talking about FLARM specifically here in a little bit. So, since we're going to talk about transponder systems first, let's be sure we understand air traffic control radar. So this is the kind of radar antenna that you would often see around a large airport. There are two antenna in this picture. The lower one, it's in red. This is what is called the primary surveillance radar. This guy transmits on 2700 megahertz. This is aircraft range and bearing from the antenna only. This does not require any equipment in the aircraft. What you're getting is you're getting the radar return off of the airframe. I mentioned that one on that first slide about the history. I also mentioned secondary surveillance radar that came in around 1960, and that's the second antenna on top. So these guys in this installation rotate together. This guy transmits on 1030 megahertz, and this is what triggers our transponder. And then it receives the transponder data back on 1090. 1090 should sound familiar when we get to talking about FLARM and the inputs to FLARM. That will become more important. And what comes back on that antenna is the data sent back by the transponder. So for secondary surveillance radar to work, it requires the transponder in the aircraft. Again, remember, ATC is focused on the heavies and they're focused on IFR traffic. So the air traffic control radar beacon system, that's a mouthful. Even the acronym is a nice jumble. This is the transponders in the aircraft and the secondary surveillance radar. They can be co-located, like the picture shows, the two antennas mounted on a common mount and rotating together. They could be separated by some distance, and then the ground architecture takes care of synchronizing the signals between the two antenna systems. Basically, what they're trying to do is produce a synchronized surveillance picture. And you can read through this faster than I can, probably. The last two, the bottom bullet, in common usage, people will talk about SSR. In the technical documentation, SSR is not the entire ATC radar beacon system. It's just the ground radar. So, but a lot of people use that term interchangeably. We have in our aircraft, we have active devices and we have passive devices. The active devices transmit something. They can be interrogated. They can be interrogated and broadcast, or they can be broadcast only. So let's talk about the active devices. So in the active devices over on the left, we have an interrogation source. And so now we're talking about the secondary surveillance mechanism supporting the beacon system. So the interrogator transmits on 1030 megahertz, and this thing is detecting and measuring aircraft position, bearing, and distance is the for the primary, and then the secondary is getting additional aircraft information. For instance, there's an ID code and an altitude in mode C. There's more data when you get to ADS-B. So it requires transponder-equipped aircraft and airborne. There are systems that do interrogation airborne. The heavies carrying TCAS or ACAS can transmit on the 1030 frequency and then receive response from transponders or aircraft equipped with transponders that are in the area that they're in the beam width of the antenna that they've got. So what happens? What's coming back? What is transmitted from the air? So the transponder is responding on 1090 megahertz. There's mode A that has 4096 ID codes. That's the four-digit code that is on your transponder if you've got a transponder. And it transmits the air traffic assigned ATC assigned code. Mode C has the mode A capability plus it reads the pressure altitude, so it's transmitting the assigned code and the aircraft altitude. Mode S, they came up with the idea of selective interrogation, so it has an address, so they could actually interrogate a specific target and get response. It transmits the assigned code, the aircraft altitude, and an aircraft specific registry code. We call it the ICAO code. You'll see that again later. And under this system, it can be individually addressed. Just for completeness, every once in a while, we don't see it in civil aviation, but you'll also see things about mode 1, mode 2, mode 3, mode 4, and mode 5. Those are beacon systems that are used by beacon systems and beacon capabilities that are used by the military. So that was an interrogated system. When we come around to interrogated and broadcast, this is where we come up with the automatic dependent surveillance broadcast system, ADSB. This is the core technology that is behind what the FAA used to call their next generation air traffic control system, which was, uh, and that brought up the 2020 deadline to have all of this equipment, all the new equipment installed. Okay, so the automatic, let's parse out the words, requires no pilot input or external interrogation. You turn it on and it automatically works from that point on. It's dependent upon an accurate position and velocity data that comes from the aircraft's navigation system. For for us, it's going to be a GPS system with WAS, Wide Area Augmentation System capability in your GPS receiver so that you can get high accuracy GPS uh, data. That's why you can't just use any GPS source with your ADSB receiver, is because it doesn't have all the capabilities that ADSB expects. Surveillance, it provides aircraft position, altitude, velocity, and other surveillance data to the facilities that require the information. The other major change that came with this is the broadcast. The information is continually broadcast for monitoring by appropriately equipped ground stations. So unlike Mode A, Mode C, and Mode S transponders, an ADSB system does not wait to be interrogated. It transmits twice per second, and it will also respond to an interrogation from a ground radar, but they put a bunch of ground towers or ground stations around. And so this transmitted information is not just going back through the radar channels, it's also going directly to towers on the ground, which are connected to the air traffic control system. In ADSB out, it broadcasts twice a second on 1090 megahertz, and it also broadcasts in response to an SSR interrogation. The flight identification, this is some of the things that can be included. The flight identification field. For most general aviation aircraft, this is the aircraft IN number. I found this out a couple of years back when I called the pattern in an airstrip that had an active jump operation. And like most of us, I was using my contest number. And the jump plane said they saw my IN number in the pattern and they were confused because they thought maybe there was another glider that they weren't seeing in the pattern. Oops. Okay, and my old glider, the contest number was the last two letters of that aircraft's IN number. So my uh, contest number, when I called in and said Fox Delta is in the pattern, my old N number was 88 Fox Delta. So I was technically using my N number. So this is just something to remember. A lot of us are conditioned to use the contest number on our aircraft as opposed to the N number. Many of us have N numbers and contest numbers that overlap, like the last two digits are the same. But just something to keep in mind when you're going in somewhere that's not a glider airport is if they are monitoring the ADS-B data and you call in with your contest number and it's not the same as the last couple of letters of your N number, it's going to lead to some confusion. The 24-bit ICO code, uh, it's been, you know, addressed and standardized internationally. Uh, so this is unique to your airframe. The first one or two or three symbols uh, in the code are to specify the country. So in hex, where we have six symbols, it's hex. It can be represented as hexadecimal, octal, and binary forms. The hexadecimal is 6 digits, octal is or 6 symbols, octal is 8 symbols, and binary is 24 bits. All USA codes begin with an A. One of the things, again, to keep in mind is US ICO codes are derived from the aircraft's N number. If your N number changes, your ICO code changes. So if you buy a glider and get a new N number assigned to it, once that N number is assigned and has been activated, you've got to go back into your transponder and change to the new ICO code that matches that N number. When we look at the other data, there's at least 18 kinds of data, types of data that are broadcast depending on the circumstances of the flight. This has got 15 of them listed. One of the things that is also transmitted is position integrity and accuracy. And this is a measure of the performance of the GPS receiver and the quality of the data in the GPS stream. There is nothing in the data fields about the make and model of the airborne equipment, that's used. There's no transponder model or manufacturer or serial number for the transponder or the GPS source or anything like that. It's assumed that your installation, you have an approved installation and it meets those needs. So they're not checking that data. They didn't need to use up the bandwidth for something like that. ADS-B has at least two modes, a ground mode and an airborne mode. If you're on the surface and you're sitting still, it sends a packet every 5 seconds. If you're moving, it sends something twice per second. If you're airborne, the surface position data is not sent. Now you're back to airborne position and velocity data, and that is sent twice per second. So one of the things that we run into in our installations is we're using the TRIG system, and TRIG has a GPS-based airspeed switch between ground and airborne. I'm not sure of why, but this mechanism has been problematic. For instance, in 2021 Nephi contest, there were reports the FAA contacted individual aircraft owners about their signals. Their ADS-B out systems were producing airborne signals while they were sitting on the ground. So from the TRIG manual, automatic ground switching is optional for a TABS application, but it is required to comply with 91.227. So surface position reporting is used to facilitate ground taxiing operations at the airport. Um, and classic TABS applications were envisioned to be like hot air balloons, gliders. So there was no benefit in air to ground switching. And so the squat switch was supposed to be configured as none in your configuration, in your transponder configuration tables. if the aircraft has a physical squat switch, it should be used for air to ground determination, but um, it seems like that the TN72 could be used to emulate a squat switch by selecting auto on GPS data as the squat switch source. Okay, the problem is I don't know about the latest versions of the software in the TT22 and TN72 combination, but as noted for Nephi in 2021, it wasn't always doing what we thought it was doing. So anyway, in a lot of cases, like in my glider, I have a airspeed switch that switches it back and forth. So um, has the GPS-based switching worked in gliders? Yeah, it has. Has GPS switching indicating ground mode while the glider is in the air? Yeah, park your glider in wave or be fighting a strong headwind, and the system might be incorrectly indicating ground mode because you have a low enough relative ground speed. I've put an airspeed switch in all of my gliders that I've owned since I started using the ADSB transponders, and it switches between the ground and air modes at roughly 30 knots. So the when I did the first test of my first installation, the flight report had indicated uh, incorrect flight mode switching. So I had in flight while on the ground, and I had to correct that uh, before they would give me a smiley face on my installation. There are a couple of ADSB out compliance methods. So the top box is talking about what you do with a standard airworthiness certificated aircraft. You have a Mode S extended squitter transponder. The ES, or the extended squitter, refers to the ADSB information that was appended to the existing Mode S data stream. It requires a certified WAAS GPS source with quality of service indication. We have one of our tow planes at our club has this type of transponder. The other one is a universal access transceiver. This can also be used with uh, standard airworthiness aircraft. It requires a Mode C transponder. Again, this is operating the transponder on 1090, but we have an additional unit in the aircraft that is transmitting data on 1098 megahertz. And in this case, um, this is sending a signal down to the ground station towers. And one of our tow planes at our club is equipped with the UAT. The I have certified in quotes because we'll talk about how this applies when we're talking about standard airworthiness versus experimental airworthiness. There is a prohibition of using both UAT with a mode or using a UAT with a Mode S transponder. And the idea is that the UAT device is installed between the transponder and its antenna. The transponder transmits in response to the ground radar interrogation. The UAT device reads that data, transmits it transmits in response to the transponder's transmissions, picking up the Mode A code and the Mode C altitude from the transponder, and then adds the ADSB out data and sends it down on the 978 link. And so in this case, what we've got is, you've got a certified altitude source, pressure altitude source with your Mode C installation, and so it's picking that data up and including it. So one difference though is if you've got UAT, The UAT device does not independently transmit like a 1090 ADS-B out system does. This is only going to transmit the data when the transponder in the aircraft gets triggered. Out example systems, if you've got a standard airworthiness aircraft or an experimental aircraft, trig, I'm going to have trig examples for pricing, and we'll talk about that here in a moment. So with the standard airworthiness certificate, you have a TT22, and trig has recently added a TT23 transponder, and those are certified at the level that satisfies ATC. You end up with a trig TN70, or a newer device is a TN70A. This is a certified GPS receiver, again, TSO certified for regular ATC use. You have a certified TA70 antenna, and then if you're for your glider, Peregrine has an ADS-B airspeed switch that is part of an STC. This is fully 91-227 compliant, and you are in the approximately the $5,000 range. So if your glider is uh, standard airworthiness certificate, then this is the equipment suite that's the FAA is expecting you to install. If you have a experimental glider, you can use the TT22, the TN72, which is certified to a different TSO called C199, and then the TA50, which is an uncertified GPS antenna. It's a little hockey puck antenna. And then you can get a ADS-B system airspeed switch. It doesn't have to be the one that comes with the STC. In this case, uh, interestingly enough, because you're experimental and the TN72 provides a source integrity level of 3, this is considered in an experimental glider a fully compliant installation, so you could fly in A, B, and C airspace with it. The cost of this system is approximately $3,000. Now, I mentioned the TT23, which was added recently by Trig. They have a TT23G, which replaces both the transponder and the GPS receiver with a single box that's about the same size as the old TT22 transponder box, the remote box itself. Now, when we're looking at the difference on the Trig hardware, what's the capability difference between the certified and the uncertified system? I've talked to the Trig engineers or the Trig representatives at the convention, and there's none. The reason for the price difference is the paperwork and testing expected and the usage for the TSO requirements. So, and a TSO, it stands for Technical Standard Order. It's a minimum performance standard for specified materials, parts, and appliances used on a civil aircraft. So the 166B that you see up there on the certificated is for extended squitter automatic dependent surveillance. The 154 that I showed on the previous page is for the UAT. The 145D up on the standard airworthiness for the GPS source is air navigation sensors using GPS system augmented by the satellite-based augmentation system. How's that for a mouthful? The C199 for the GPS source and the experimental is the traffic awareness beacon system. So if you've heard tabs, that's what it's talking about. And then tech order or TSO C190 in the certified for the antenna is active airborne global navigation satellite system. So there's tons of these standards that apply to this equipment, And there was enough interest in getting traffic awareness for experimental airworthiness aircraft that folks and companies jumped through the hoops to create the standards that gave us an alternative implementation as opposed to having to buy and utilize the full certified system. ADS-B in services. So this is provided by ADS-B ground-based transmitters or transceivers. There are three services that are provided: Traffic Information Service, TIS-B, Automatic Dependent Surveillance Rebroadcast, ADSR, and Flight Information Services Broadcast, so FIS-B. Okay, these are in general, these services are ground to air. Um, so if there's processing that happens, there may be a delay. Air-to-air signals, so you can receive some ADS-B data directly from another aircraft, so you can receive its transponder output. That's near real time, or as close as you can get with the, and especially with the distances that are involved. Ground to air signals can have an undetermined delay. So one of the things that happens is the some of these services are going to be putting up targets for you. For instance, TIS-B and ADSR take signals and retransmit them so they can be received by the aircraft, but they may have an undetermined delay coming back to you. And so we end up with this thing about that the information received both air to air and air to ground by an ADS-B in receiver is for situational use only. And the ADS-B out, mandated for U.S. airspace Class A, B, C, and above 10,000 feet, requires a SIL 3, so source integrity level 3, to ensure a high probability of position accuracy. And then there are performance measurements. So along with the SIL 3, that the source is sufficient, has sufficient accuracy capability, that the aircraft must maintain a navigational integrity category of less than 0.2 nautical miles, so 1,215 feet. Okay, that's not fine enough resolution for us to be using directly for collision avoidance. So that's why those two things bring forward why the FAA is saying that the information that comes in on the ADS-B in channel is for situational awareness only, not to be directly used as a collision avoidance. So basically, we're still back to collision avoidance is being handled, even in the ADS-B environment, is collision avoidance is still handled by the air traffic controller. Now, what do those terms I just mentioned mean? Okay, TIS-B, this is what is called a client-based service. So if you've got ADS-B out and in, you're talking to the ground station, and there's a target out here. There's a Cessna 172 out here with his Mode C transponder or maybe his Mode S transponder, but he doesn't have the GPS source to be an ADS-B user. So most of the time he wouldn't be seen. And so his stuff goes into the ground system, is brought across, and then transmitted out either on a UAT frequency or on the 1090 frequency. Now, this is a old FAA slide, and so they were saying UAT was general aviation and 1090 were the big guys. Well, we're all flying. A lot of us are flying with 1090 transponders. So I'm just pointing out that it comes out both links. And so this is a way to get the non-ADS-B user out here visible to us for situational awareness. If there's an aircraft out here that is only responding to the primary surveillance radar, it does not have a transponder, that does not get forwarded through because they don't have the altitude information. When it comes in with the mode C transponder, you've got the fully resolved, based on the ATC system, you've got the fully resolved position. And so they can send that to us and have it be useful. If this guy out here has no transponder and is only responding to the primary surveillance radar, then all they have is a range and an angle from from the transmitter site. And so they can't really forward that to us as a useful piece of information. The ADS-BR, this is rebroadcast. So one of the things that happens with this is if you've got 1090 and you're transmitting, but this guy's running UAT on 978, they can't hear each other. So one of the things that happens with this is the 1098 transmits, ground station receives it, translates it to 1090, and sends it up. The 1090 comes down, gets translated, and then up on the UAT frequency, the 978. Okay, so this is a relay system, but this starts to show that if any delay down here, as opposed to being able to directly receive between these two, you don't know how long it's spent down here. So the data that comes up is, the position's going to be off by some time period. Now, is it significant? Engineering answer, it depends. So this allows the 1090 ES user to see a UAT user, and it allows the UAT user to see the 1090 user. All right. To receive ADS-B in traffic services, you've got to be, and this includes the passive systems. Okay. The aircraft has to be equipped with an ADS-B in receiver, and then it can receive weather and proximate traffic. The most reliable traffic information is air-to-air via ADS-B, so 1090 to 1090. Aircraft not equipped with ADS-B out, the ground station will not identify them as a client for the TIS-B or the ADSR services. However, if you're flying near an aircraft that has ADS-B out and they've said they want to receive the signals, then they can trigger it and it's available to you. Okay. This includes the folks that have got the passive systems like the Stratix and stuff like that, and we'll talk about those later. So to be considered a TIS-B or an ADSR client by the ground stations, by the ground transceivers, it's got to be in a region where the services are offered. They're not offered in all locations. It has to be ADS-B out equipped and produce a valid position data within the last 30 seconds. So if you quit transmitting, it's going to quit talking to you after about 30 seconds. And it has to have ADS-B in on only one of the links. So if you've got an aircraft that's got the mode C plus the UAT, okay, then the UAT is your only in link. But you're only going to pull this data in either on your UAT or on your 1090. You're not supposed to be trying to pull this traffic services on both. The flight information system. This is probably one of the neater things that they did come up with. Flight information broadcast. This provides meteorological and aeronautical data to the cockpit. This is not client-based. In other words, it's always being transmitted. And this information is only transmitted on the UAT frequency, so 978 megahertz. It is not transmitted on the 1090. Okay. So if you want that, you've got to have one of the passive systems to pull that data in for you. I'm not really sure that it makes a whole lot of sense in a glider, but that's the case. So some of the FIS-B products that are available is AirMet, SigMet, and convective SigMet, the METARs for the ground stations. You could get CONUS NextRad radar, regional NextRad radar. You could get NOTAMs and PIREPs, special use airspace status, terminal forecasts, winds and temperatures aloft, and the status of the TIS-B service, whether it's up and running. So there's some useful things there, but again, I'm not sure how much I would be willing to put another receiver in the aircraft and another display. Uh, my cockpit's rather busy as it is. So today, ADS-B is required for certain airspace. Mode C and Mode S in the United States are not being phased out. So if you've got it, continue to use it. When it comes time to replace it, consider replacing it with an ADS-B system. But there's not an end date for Mode C or Mode S. Okay. When we talk about certain airspaces, we think of Class A, B, and C, and the E airspace above 10,000 feet. Um, okay, so now here's an example based on our area. Um, Years and years ago, probably more than 30, I was somewhat resistant to putting a transponder in my glider because I didn't see the need for it. And but what's happened is our airspace has gotten really, really interested in our area, and I'm interesting in our area, and I'm sure that this holds true for others. Okay, the green circle, that's Kelly Air Park, Black Forest Soaring Society. And to the north, we've got Denver International, which at one point was the fifth busiest airport in the United States. We've got Buckley Space Force Base, which has a Air Guard unit flying F-16s and Army uh, Guard aviation, so lots of helicopters. Centennial Airport is one of the busier general aviation relievers for DIA, so it's got a lot of heavy and fast, heavier, not 737 heavy, but you know, large large jets that aren't Part 121 type, not airliners. To the south, we've got Colorado Springs Municipal. The airspace around Denver International is Class B airspace, and the airspace around Colorado Springs is Class C airspace. So basically what we've got four airports within 40 miles that handle heavies or fast movers, and they generate lots of traffic. The terrain over here to the west quickly goes to 10,000 feet. Our field elevation is 7,000 feet, but in the Denver area, stuff is 5 to 6,000 and roughly the same down in Colorado Springs. The terrain over here quickly rises above 10,000 feet and go a few miles further over, and it quickly gets into the 12 and 14,000 foot range. For instance, the mountain that's right here that you can see the dark for, that's Pikes Peak and is 14,110 feet. So we get a lot of traffic compressed in this corridor right here. And you can see a lot of the Victor Airways, but this is a sectional, so it's not showing the standard instrument departure or the standard terminal arrival or approach routes to any of the airports mentioning. It's a really complex airspace. All of our club gliders and tow planes have transponders. I think we may have completed the effort, but we were upgrading all of our club gliders to ADS-B out. One of our tow planes has ADS-B out on a UAT, and the other has ADS-B out on a 1090. Almost all of our private gliders have transponders, and many of them are ADS-B out. And this is increasing as equipment changes. Either they're changing out older electronics in their panel, or somebody's buying a new glider. The other thing to point out in this area, this is the Air Force Academy. They have high glider activity. And over here is the Meadow Lake Airport. Notice the cutout in the Colorado Springs Class C airspace. That's got heavy glider activity. And then, although there are no clubs associated with Colorado Springs East Airport out here by Ellicott, this has been a popular place for people to go for winch launching and to have off of their home airport uh, training experience. So it's a complex world out there. The ground-based transmitter transceiver system. Uh, this gives you an idea. Supposedly, the FAA has said, or no, not supposedly, they've said, the FAA has said they have built out the complete system, that they're not planning on adding any new ground-based transceivers. You can see the density, like here's LA Basin, San Francisco, Chicago, Minneapolis, the whole Northeast Corridor, uh, Cleveland, Detroit, coming down into the Charlotte area, Atlanta area, Dallas, Houston. This is an interesting because of the high mountains. Again, Colorado's got 54 peaks that are above 14,000 feet and a whole bunch of them that are above 13,000 feet. So there's a real concentration of towers in the mountainous terrain to be sure that they've got adequate coverage. There's less out here when you look over into Utah and Nevada. That doesn't mean they don't have adequate coverage. Flying out of Nephi, which is south, oh, let's say roughly about where I've got the cursor right now, we've got ADS-B coverage out there. Okay, so just because there aren't towers, a whole bunch of towers, the terrain is such that they didn't need to put in as many towers as they did in the mountains. Okay. Um, the towers are split between three categories. There's low, medium, and high. The difference is how far they provide services out and what services they provide. So, for instance, Cessna 172 at 3,000 AGL has different needs than a 777 at, flight level 350. And then there are surface GBTs, ground-based transmitters, at busy airports to support ground operations so that they can control taxiing and stuff like that. In our area, you can find this, you can probably, this data you can find for your own local airport, uh, but I pulled this up. Uh, Coverage for most of Colorado starts at about 500 AGL. Here's our home airport, and there is a ground-based transmitter, or transceiver, sorry. There's a little town right about here called Elizabeth. Um, this ground-based transceiver is northwest of Elizabeth, about 15 miles north of Kelly. And this ground-based transceiver, uh, there's a little town down here, Calhan, so southwest of Calhan, about 20 miles southeast of Kelly. One of the things you have to remember is that ADS-B out is not radar dependent. The aircraft is transmitting the signal twice per second. Interestingly, when we've asked for the performance reports as we've upgraded aircraft to ADS-B out, the ADS-B system can can show ground movement on our airport at 7,000 feet MSL, including taxi, takeoff, the transition to the air on takeoff, and the complete landing phase upon returning to the airport. So they see your rollout, the stop, and then if you haven't turned your transponder off, they'll watch you taxi back as you get pulled back behind the golf cart. ADS-B out advantages. It makes us visible to the widest set of national airspace users. I have actually seen airliners that altered their course to avoid where I'm located, and that makes me feel really good. The limitations, The information that is received both air to air and ground to air by the ADS-B receiver is for situational awareness only. It is not considered to be sufficient for real-time collision avoidance. Automatic dependent surveillance rebroadcast limitations. Okay, as I said, there has to be a client who is requesting the service. The service that is being provided is providing information for the airspace plus or minus 3,500 feet from the altitude of the aircraft and a 15-mile radius around the aircraft. If you don't have ADS-B out, but we've got ADS-B in with our FLARMs if you've got FLARMs installed, or you've got one of the passive systems installed in your aircraft. If you're within that hockey puck from somebody requesting the service, you'll receive all of that data. Okay. So anyhow, that's the limitation associated with getting the rebroadcast data. All right, broadcast services. Now, we're shifting from air traffic control and and transponders to the peer-to-peer system that we've come up with for gliders that we're using in the United States. These devices are not part of the air traffic control system. ATC knows nothing about this. There's no interface. So this is only providing you protection when you're talking to another equipped aircraft. So you can see the derivation of the term up there in the first line. When I talk about power FLARM or FLARM, I'm talking about the US centric FLARM product variant specifically created for the USA market. Right now, I think the models are portable, the FLARM portable, and the core, FLARM Fusion, and FLARM Flex. Okay. If you don't have a FLARM unit installed in your aircraft or something that can process FLARM data, then your aircraft is not a participating aircraft when it comes to FLARM. Older units can be upgraded to ADSR and TIS-B activation. Newer units have that capability from the factory. But you have to, for the older units, you have to buy a activation license from one of the vendors in the US. So, Craggy or Cumulus or uh, Wings and Wheels. I should probably put that in my notes. If the services are available in your area, ADSR makes UAT equipped visible to the power FLARM. So, you could get the retransmission of a UAT if you're in the donut or if you're in the hockey puck or if you've got ADS-B out. And TIS-B uh, turns mode C and mode S non-directional targets into a full 3D target. So purchasing that upgrade for your software, that license upgrade for your software is probably worthwhile. When we're talking about this, we've got various displays. It's dedicated and multifunction, so you could have a dedicated FLARM display in your panel, or you could have like an LX9000 with the FLARM display layered on top of it. Generally, these are wired connections because this is going to be a high-speed channel. Commonly, the dedicated displays use what's called a pseudo plan position indicator. Like in the old movies, and they showed the radar set with the radar in the middle and a line going around and going around the circle. It gives you a plan view position of the area. The multi-purpose displays can use map-based presentations where they're putting it against the map background and don't necessarily have the overlay that the little radar, pseudo radar scope would have. So we've talked about this. The ADSR and TIS-B capabilities were added in 2021. And then you can have also the systems in the United States can have an IGC approved flight recorder with an engine noise sensor. If you may need to buy an activation license, or if it's a later model, it may come with that already enabled. The current software is 7.43, and that was released on February 6th of this year. If you've got a FLARM installed, keep your software up to date. In February of 2024, FLARM, the company, announced a revision to their firmware versioning policy that allows older releases to remain active beyond their original 15-month cycle. It does, in order for this to be enabled, it does have to be a version of the software that is well after that date. So probably the fall release in 2024 was likely the first one that didn't have the expiration on it. FLARM processes three different types of targets. It processes a FLARM target. It processes ADS-B out targets, the 1090 targets, and it also processes PCAS. That stands for Portable Collision Avoidance System. That was a specific system that was the proprietary system they came up with years ago, and the FLARM documentation uses the term PCAS to denote non-ADS-B out transponders. In other words, mode C and mode S transponders. So when you're looking in their documentation, just realize that that is what they're using that term for. It's kind of lost its original definition. Okay, this is a LX FLARMView nav display, or FLARMView. Let's try that one again. This is an LX nav FLARMView display. So I'm just using it as an example. This this display is showing three targets. We got a green target, a red target, and then this ring of dots. So one of these targets is a FLARM target. The other target is an ADS-B target. And the third target, that ring of dots, is the PCAS target, or the mode S, mode C target. And the reason it's a ring of dots is there's no altitude information, but they have calculated an approximate range. So you don't know which direction it is, but like in this example, since we're at a zoom level of 1, and this particular display, I pulled it from LXNav, so everything's metric. So this is a 1 kilometer across. So in this particular display, about a half a kilometer out, there's or 1 kilometer radius. There's about 1 kilometer out. There's somebody that's reporting as a mode S, mode C, or mode S. Okay. Default colors. Okay, green is for an aircraft that's below you. The little memory aid is, think of green grass below you. Red is pretty close to your elevation, so you want to, be on the lookout for that guy. And if it's blue, again, your memory aid is, think of blue sky above you. The white dots are a non-directional target. The blue circle means you have selected this target, and the data that's displayed over here on the left side is the data associated with that target. We'll go down through that here in a moment. Up here in the top, the status of the FLARM. The TX means that the FLARM has initialized and is transmitting a signal. The 1 means it's receiving one FLARM target. Okay, notice there's 3 targets on the screen, but you're receiving one FLARM target. And so this will be 0 or greater. If you're sitting on the ground not moving, it's north up. If you're moving, then it's heading up. The FLARM identifier right here, this DD9C78, what that tells me is that's the FLARM factory radio ID. The default for the FLARM is they've set a radio ID, and it's following the ICAO convention of 6 digits. And most of us are setting this to the aircraft's ICAO identifier. If you've got ADS-B out, you actually need to set your FLARM to your aircraft's ICAO output because otherwise you're transmitting from the FLARM and from your transponder two positions that are in essence the same. They're close enough to be the same. They may not be exactly the same, but they're close enough to be the same, but they're with two different IDs, at which point the processing is going to go absolutely nuts. There is a crowdsourced mechanism called FlarmNet, which is a database that takes your ICAO address and information about your aircraft, including your contest number. And if you've got that database installed in your display, then instead of displaying this uh, radio identifier or your ICAO identifier, it will display your contest number. So, and you can have it to where you can generally have it to where it displays that data right next to the target. So you could have a contest number right next to this green target. The other stuff that's here is distance to the target. Uh, the current vario of the target, is it going up or down, and its relative altitude to you. And then the other one over here is the zoom level. And then there's usually an indicator in the corner somewhere that says how your GPS receiving is. So on the FlarmNet, we'll talk more about that in the flight tracking seminar on the 21st of April. So the reminder down here is you're probably well served to put your aircraft ICAO identifier in the FLARM as the radio ID and then register it with FlarmNet so it helps the people flying around you to identify you. Other displays, this display will pop up if you've got an important or very urgent alarm. This is saying there's somebody of real interest out here in this case, 659 meters away from you. It's red, and this is saying, it could say look up 10% or down 10 degrees, up 10 degrees. This is saying he's at your altitude. There's someone behind you, so you can't really tell whether that 659 is the one in front or the one behind. And then there's somebody out in front of you, but it's not as urgent about that one. This display is there's someone 233 meters back behind you at your elevation, but it's not a urgent problem. So the so you've got red is urgent, yellow is yellow, or in this case it looks orangish to me on the screen, is not so urgent. The number in the middle is the distance. Over here, this is a PCAS warning, so non-directional, mode C or mode S. You know, it's out there and it's close, but we don't know which direction because we don't have the position for it. All we've got is range, range and altitude. And then FLARM added a ground obstruction database that you can have as well. I don't know if that applies to the US or not. That the database applies to the US. The capabilities in the firmware, but I don't know that they've actually got an obstacle database for the US. This is probably the scariest display that you can have. That full red dot in the middle. Notice the zoom level is now out to 5. That full red dot in the middle indicates that there is a non-directional target too close for the screen that at your zoom level to put a ring of dots around you. And you don't know the direction, and you got two others up here that are red, but that red dot right there, if I felt like I had time to do something, I'd probably reduce my zoom level down to see if this says, oh, he's a mile away or a kilometer away using their notation for this one. But you've got other problems here as well. But that's got to be the most terrifying display I ever have come up is I've got a red dot sitting on top of me, which means there's somebody really close and it can't tell me which direction to look. So you remember I called this a plan position indicator because we're looking down on the top like it's a plan view drawing. This is an example from XC Soar with their display. They're not as cute with the graphics, so you just get triangles. Um, and the blue one is the one that's selected. Notice here that this has got a contest number, and the distance, the relative altitude, and the vario are arranged around the corners. And this is real common with even dedicated displays other than the FLARM view displays. So you're in the middle, and the slightly grayed out is pointing north. So, but this aircraft is in, these are in relative to you. You can also get the FLARM displays if you've got a map background. So here's one coming in from behind, and he's plus 3.5. Somebody's in front of you. The one on the right is a display from an ODI. So your aircraft is right here, and you've got other, the green line's your track, but you've got others, so that everybody's probably flying roughly the same task. So how does Power Flarm work? It has an internal GPS, so it's got location, altitude, and airspeed. As far as I know, the GPS in the FLARM is not WAS capable. So it's not a suitable GPS source to use with an ADS-B system. It broadcasts position, altitude, and speed along with a 30-second flight path projection. The receiver listens for the FLARM devices, processes the information received. The motion prediction algorithms in the receiving FLARM determines if there's a potential conflict. It can work with up to 50 aircraft. Uh, I would suggest that if you had your display cranked to where you could see 50 aircraft and it was providing something for all of them, that maybe you zoomed out too far. Either that or it's Nephi and you got 65 aircraft sitting next to you on the ground. It alerts the pilot using a visual, and if you've got some kind of tied into a speaker somewhere, it can provide aural warnings. It also has an internal barometric sensor that is used for IGC flight recorder. Okay, that's FLARM. Now we come up with soft RF. Okay, soft RF is a DIY Internet of Things based uh, solution. It is FLARM compatible. Okay, it doesn't mean that it is fully compatible. It can use it. It's good enough to be useful. Okay, but it's not this. It doesn't process exactly the same as a FLARM. It's using FLARM's air. I've got an update to this, but it uses FLARM's Air Protocol version 6, and it produces NEMA data, so it could be used as a GPS source for your tablet. If you had a tablet in the cockpit that didn't have a GPS, you could use the FLARM data, the NEMA data, to have the GPS data for your tablet. It does support being able to talk between or to move the data between the radio frequency, the data, and Wi-Fi. It's standalone. It can be battery powered. It could be provided power by the aircraft. Um, Again, this is the same as FLARM. Is soft RF requires everybody to have either a FLARM or a software RF unit in their aircraft for it to work. The physical display device may have one, or you can hook your tablet to it using a fixed address. You can do it with Bluetooth. Um, the display capability really depends on the software installation on the unit. There is no integral ADS-B or mode CS transponder receiver. Okay, so basically the uh, you get down here. Basically, this is the original FLARM capabilities uh, without an integrated display. This is what the various units look like. You notice that some of them do have an integrated display. They're using a monochrome display. The ones that have the very small screens, those are actually status screens. Uh, Most of these you buy a kit and then you 3D print your box for it. Soft RF considerations, okay, for its RF system. Now, the ISM band, which is the frequency band in the United States that FLARM operates on, is unlicensed. And so these boxes have not been tested by the FCC. It's basically a software-defined radio, and it appears to operate in the same manner as Power FLARM, i.e. it appears to be a spread spectrum system. I've connected it to XC-SOAR LK8000 and CU Mobile. Um, I've ground tested it at our home airport running XC-SOAR on a Samsung tablet with Wi-Fi to soft RF. I've also had the Power FLARM installed in my Ventus, or the Ventus I used to own, and they could see each other and report things with no problem with me walking around on the airport. I have tested the system at Kelly. I haven't found any evidence that, looking online and stuff like that, that it creates problems while operating in a Power FLARM environment. As far as I know, there's no interference between the soft RF implementations. A gentleman in the Northeast, and I'm going to mispronounce his name because I've only seen it written. I've never heard it, but I'm assuming Moshe Branner has been providing new soft RF software firmware builds over the last couple of years, and he's expanded the capabilities. He's doing both the aircraft box, and he's also doing stuff for the OGN network. And so I find that interesting. His firmware supports at least FLARM Air Protocol version 7, which is the 2024 version. And he has identified hardware that can add ADS-B and mode CS capability to these devices. It's actually a fairly simple addition. Plus, he's also identified candidate improved GPS receivers, and all of that increases the footprint very little. Matter of fact, at least the ADS-B, the 1090 receiver, can actually fit inside one of the boxes with just a little bit of one of the current 3D printed boxes with just a little bit of work. Um, so this might be a good approach to adding FLARM capability to club gliders if you wanted to do it and not have it be, you know, $1,500 or $2,000 per aircraft. The basic circuit board with the antenna starts at about $40 on Amazon. You'll need a case. So if you know somebody that's got a 3D printer, you can get the print files on Thingiverse. There's services out there that you can pull one of those print files and take it to them, and they'll print it for you, send it to you for a fee. So there's ways to get it. Now, one thing when we're talking about soft RF, and I am not picking on anyone. I just want to be sure that you understand before you get wound up and say, hey, I want to try this. My instructions to you is going to be go to GitHub and search for soft RF. If those instructions are insufficient to get you started, then this might not be a good approach for you. Now, there's probably somebody in your club that knows exactly what that sentence means and can jump on it, you know, like anything, and be real happy to go off and take a look at this and see what they can do. But if that statement is kind of confusing to you, you're probably not the good candidate for this system because this is a do-it-yourself uh, and requires maintaining this, keeping the software updated and staying up on what's going on with all the evolving changes. And the key here is since this is DIY and it's crowdsourced, you don't have a company like FLARM sitting in the background doing all of this for you, sending you and going and checking their website to see if there's an update and everything is ready for you. All right, let's talk about passive devices. Okay, there are a lot of dual band ADS-B in receiver systems out there. These devices are receive only. They can be configured so that they can receive both the 978 UAT, UAT, quit trying to pronounce that acronym, the UAT system and the 1090 system. It can receive TES-B from the ground station. It will only receive ADSR if there's an ADSR client nearby or if you happen to be an ADSR client. It does, most of them, I think all of them require a external display. Um, these are receiving ADS-B in signals. This does not work with FLARM. I know that there is in some cases an effort to try to get a crossover, but right now just take it that it doesn't work with FLARM. These are available as complete units, or in some cases they're available as a DIY kits. You might have to 3D print a case, or you might be able just to order it and assemble it. But like you notice on all of these that they want an external display of some type. All right, new section this evening. Visual collision avoidance. Way back on slide 10, I said the big sky model is inadequate for aircraft separation. I also said that see and avoid is no longer sufficient methodology for collision avoidance. It's no longer a singular sufficient methodology for collision avoidance. Okay. Now, I'm going to apologize. I'm going to take this off into the personal realm for just a couple of minutes. Years ago, while on tow, a sailplane passed between me and the tow plane, barely missing the tow line. That is not an exaggeration. I was focused on the tow plane. The other glider pilot was low and had airport tunnel vision. I had a conversation with the pilot later. I had calmed down and that kind of thing. The pilot never saw us. Okay. That's my point about see and avoid is no longer, the singular sufficient method for collision avoidance. And big sky is a roll of the dice. The other incident, which is why I'm bringing this up, last year I was self-launching. I was about a mile out from the runway at my home airport and had a near midair with the returning tow plane. How near? I was wondering if the right wheel on the tow plane's landing gear was going to hit my tail as it went behind me. Okay. So neither incident was a head-on path. They were crossing paths. The first one was at 90 degrees, and the second one was, by the time we saw each other, about 45 degrees from the front on my right, so on the front on his left. We did see each other. We did make slight alterations, but by the time we saw each other, we were so close that, for instance, if I had banked up hard, I would probably have hit his wing with mine. Okay. So one of the things that I've been working with for the last few months is how do I make my glider more visible? And basically, what I'm coming around to is flasher systems. Um, if I don't see the airplane having bright neon colors on my plane, don't help. It doesn't help to have bright neon colors on the tow plane if I don't see the tow plane. What's interesting is I didn't see the strobe on the tow plane. So I'm not sure that I'm not saying this is a solution. I'm just saying this might be a help. I'm avoiding calling these flasher systems strobes because they're using LEDs, not strobe tubes. Schleicher offers an LED flasher embedded in the vertical fin as a factory option on their new gliders. I've seen at least one of these at a camp, but I've never seen one of these operating in flight. So the other one is there are various vendors out there that are offering field installations for LED flashers, and these seem to be canopy flashers. And then at least one manufacturer is doing top and bottom LED flashers that have got a 360-degree ring around the glider field of view. So you can mount one on top, one on the bottom, or both. These flashers are independent, or they can be FLARM connected devices to where it changes the flashing in response to FLARM warning level with either increased flash duration or increased flash frequency. I have seen canopy flashers in the air, and I've been impressed with how visible they make the glider. You've still got to be it's really concentrated. One vendor has a profile that says the strong flash is 18-degree cone in front of the aircraft and a 30 with a 30-degree uh, peripheral flash, or so it's a total of about 60 degrees on the lighter flash with the real strong flash at about 18 degrees wide. Um, so I'm impressed enough with this that I'm adding this. I'm adding a canopy flasher to my glider for the 2026 season. I doubt a flasher would have helped in the first incident. I'd like to think that it might have helped in the second incident with the focus as I came out of the turn and maybe put the nose across the glider. The fact the manufacturers are saying that even in bright sunlight, these may be good out to about 3 to 3.5 kilometers. I do know I've talked to people that have seen them in use on ridge soaring, and they were very impressed with the ability to find a glider in the distance with the flasher before they could see the glider itself. Okay, collision avoidance integration. TCAS uh, is integrated in heavy aircraft, think air transport aircraft. It detects possible collision events and it issues traffic alerts and resolution advisories. So it will give an indication to the pilot up, down, left, right, that kind of thing. Get away. ADS-B in, its integration, it does not intrinsically detect possible collision events. Okay. You might have it connected to a device that does, okay, like the FLARM. It does not issue traffic alerts. It does not issue resolution advisories. Remember, that's an ATC function, and the collision avoidance is provided by the ATC controller on the ground. Powerful alarm detects possible collision events and issues traffic alerts. It does not issue resolution advisories. It doesn't tell you which way to turn. It does integrate FLARM, 1090 for ADS-B, and 1090 for the non-directional transponders, the Mode C and Mode S transponders. The alerts are sent from the Power FLARM unit to the display device. Power FLARM version 7.3 added the ADS-B in capabilities for TIS-B and for ADSR. So um, my glider has an ADS-B transponder and a power FLARM. So, and they're interconnected, and I use the FLARM display in my S100 for the display. Plus, I have it displaying on my tablet, and my tablet runs XC and it also runs Navigator. Um, and so, I have it display the traffic information. I find that the FLARM display on the S100 is gives me much more information than seeing it on the tablet. LXNav, when you put the FLARM information to the tablet, it actually will display warnings, which Navigator and XC are not displaying warnings. So the information for my Android tablet with XC and with Navigator, the FLARM information on the tablet is purely situational awareness. My traffic conflict information comes from my S100. Okay, some last thoughts as we wind down. Almost everybody that adds Power FLARM to their glider makes a disturbing discovery. They become aware of how much traffic is out there that they're just not seeing. Okay, they've never seen it. The other thing is they learn how hard it is to spot the traffic the device reports. Um, it's out there, but if it's not real close, you have to kind of figure how are you using this thing. So you need to practice spotting the traffic based on if it says there's somebody out that's a mile and a half and they're 30 degrees off your heading at about your altitude or 1,000 feet below or 1,000 feet above, you've got to practice finding them. Okay. What I normally do with mine is I run mine at a mile and a half or 2 miles when I'm in the airport facility, and then I run it out at about 5 miles or maybe a little more when I'm away from the airport. And then anytime I come into an airport area, I dial it back down to, I can't remember whether it's a mile and a half or 2 miles. Okay, almost everyone who has a FLARM system failure finds out how vulnerable they feel without the FLARM. They're it's really uncomfortable. And then the other thing that they realize is how much their visual scanning skills have deteriorated. So no matter what equipment you've got installed, you've got to keep your visual scanning skills current. You've got to keep doing it. Just having these devices, not everybody has something that will respond to any of the things we've talked about. They're still operating in the big sky and see and avoid. And so that means that even with the help of all of this equipment, no matter what suite of it you have installed, we're still back to big sky and we're still back to see and avoid. And I mean, it makes life easier. Like you go out, I've gone to uh, OLC camps at Nephi, and I've gone down to Moriarty and flown down there, and there's a lot of gliders around, and this helps. But you've got to still be able to see the ones that are out there that are close to you that are going to be an impact. I'm sorry, wrong, poor choice of words that could have an effect on your flight. You still need to be out there scanning for them. All righty, we're down to questions.
All right, Dave. We've got well, now a third one just popped up, but the first one goes back to our first hour, and Mark is asking, does MLAT use SSR to detect position and altitude?
Oh, you would have to ask that question. No,
No,
it does
I
not.
didn't ask it. The
No,
other
no, no.
Mark asked.
No, no. MLAT is using the 1090 signal to disambiguate the position. So it's a set of receiver antennas, or it's an antenna system that's using the 1090 transmission to disambiguate. So it's not specifically using the SSR side of it, but it is using the 1090 signal off
Oh,
off of the transponder.
okay. Is that sort of, and this is my question, is this sort of like what you were talking about, the GBTs and the ground-based
No,
uh,
the GBTs,
transmitter antennas we're seeing on the Western Slope?
no, those are specific for ADS-B. The MLAT was there are some issues. Uh, there are some radar issues that are associated with the SSR that the MLAT is being used to try to get rid of an ambiguity that they observed when they put it into service. And so this is actually a different set of antenna.
Okay. Brian is asking if you could give a quick summary of the ATC confirmation process for a new ADSB out installation.
Okay. The confirmation that you've got to, okay, the first off, you've got to have the sign off of the mechanic that the installation is uh, that the installation has been properly done. The second thing you've got to do before you turn this thing on and start using it is you've got to have the uh, I can't remember the FAR part number, but the or the parts section, but you've got to have the radio shop do the test on it that it is producing the correct signals at the correct power levels. Okay, so you have to have that stuff done first. Then you go out and fly. And what you want is a flight that is a minimum of 30 minutes in an area that has the ground-based receivers, the ground-based transceivers, so that they get a minimum of 30 minutes of data. And then what they're going to do is they're going to look at the quality indicators um, because there's a setup like on the trig. There's I don't remember how many parameters, but there's a bunch of parameters that you set about your aircraft and about the equipment that you've got installed. Like that, do you have do you have a SIL3 data source? And what are the thresholds for the performance stuff, the performance measures? And then they're going to record you for a half hour. They want a minimum of a half hour and then you come back and land, and then you go on the FAA's website for the PAPR. And I'm sorry, I don't remember what those stand for. The Airborne Precision Report or Position Report, something like that. But it's
Yeah.
called the PAPR, and you get it from the FAA's website. Give them a half hour to an hour, uh, uh, and then go in and pull the report, and then it will show you uh, if everything's green or if there's an area that there's a problem. And generally, if there's a problem, it doesn't mean that you have a, a, a malfunction in your system. You may have a setting that's not set correctly. And especially if you've got trig, the guys at Midwest or Mid-Continent over in Wichita know what all the problems are when you if you call them and said, "Hey, I got this," or if you've got somebody that's whoever your local avionics geek is, if they've been playing with this, they can help you. But that's basically the process. When I did my Aventus originally, I didn't have the air to ground switch, and I didn't have the software set properly either. And it was funny because those towers, they're 15 or 20 miles out from Kelly. I turned the transponder on before I left the hangar, and we towed out to the end of the runway, and then you could see it go. So you could see the tow out to the end of the runway, the cross the taxiway on the runway, the takeoff roll, the takeoff. You could see all of that, and then that's when I got the message back that, by the way, you were sending airborne stuff on the ground. I fixed that, and then you could actually see it switch from ground mode to air mode. But there's no specific approval. What your obligation is to correct the faults that are found in the report and then do another flight. And once you've got a clean report, it's not required, but I stuck that in my glider paperwork my documentation folder for my glider so that I had at least one clean report uh, before I started using it on a regular basis.
Okay. Two questions on OGN. One is, can you discuss OGN? Um, and the other one is, can OGN, the soft RF signal be detected on FLARM?
Okay, OGN we're going to cover in detail on the session on the 21st because that's part of that's the glider tracking session. So
Okay.
I'm gonna push OGN off to there. And the other one is soft RF is using the same frequencies and the same schemes as FLARM. And so FLARM will see soft RF devices and soft RF devices will see FLARM.
Okay. Another question is I just changed my tail number. Is a full recertification confirmation process needed?
No, just get your the ICAO address associated with your tail number into your you got to get it
Transponder.
into two places. One is into your transponder settings, and then the other is if you're on FlarmNet, get it changed over there so that the radio ID code will then still match your contest numbers.
Okay, cool. Finally, Eric is asking about any comments on a device, and he gives me a web address, pilotaware.com. So he's probably talking about some kind of device. I don't have a chance to look at that yet, so I'm not quite sure what he's talking about there. Um,
Well, FlightAware is
no, it's not FlightAware, it's
oh
Pilot Aware.
PilotAware.
Pilotaware.com. I can't jump out of here and look at the website. So
Give me a second. Oops.
Pilot Aware FX, it's called. It's a device. Hang on, Eric. We're all furiously looking it up.
Yeah, we're all furiously looking it up. Um, okay. Multiple inputs. Okay. This says it can take ADS-B, ADS-L, which is a capability that's widely used in Europe, but not in the United States. It says direct device integration for FLARM. I don't know if that means I've got to plug in or if it will receive the signal. It also says mode S. So let's, all
I think
right.
this question came up last year, and I believe it's a European system.
Yeah, maybe oh, it says FLARM visibility can be supported when a compatible FLARM device is connected to the PilotAware FX. So it's not receiving the over-the-air signal.
Okay.
And it says it's ADSL compliant and it lists an EASA uh, document. So that yeah, you may be right. This may be a
Yeah, and I'm
European
seeing the
device.
EASA stuff now. So, Eric, I don't think that's good here in the US, but that's something where we can follow up on. And that's it, Dave.
All righty. Well, thank you, everyone. Um, oops, I gotta see if I can get back in control here. Ah, there we go. So next time, April 9th, we'll be talking about model-based weather forecasting, and I'm I'm looking forward to prepping that one because I've just seen a whole bunch of stuff that SkySight says that they're adding or they're saying there's some really neat changes coming in SkySight. So I get to spend the next week or so sorting through that to see what they've added to their system. Uh, Everybody, thank you for being here tonight and have a good one.